Part 2: Roots in Engineering and Science. Roots of equations frequently occur in the area of design. Mathematical equations or models derive from this principle of employed to predict dependent variable as a function of independent variable, forcing function and parameters. Graphical method. A simple method of obtaining an estimate of the root of the equation f of x is equals to 0 is to make a plot of the function and observe where it crosses the x-axis. So, I provide a simple example of the graphical approach so you can easily understand. Next, bracketing methods and initial guesses. The two major cases of methods available are distinguished by the type of initial guess. So these are the two. Bracketing methods, as the name implies, these are based on two initial guesses that bracket the root that is or on the side of the root. Second, open methods. These methods can involve one or more initial guesses, but there is no need for them to bracket the root. So this is the example. We have four example of bracketing method and initial guesses. Next, bisection. The bisection method is a variation of the incremental search method in which the interval is always divided into half. If a function changes sign over each interval, the function value of the made point is evaluated. So this is the example. Simple example of bisection method. And in first alteration, in every iteration, it divided into half. So first iteration is first iteration is 100. So the second iteration is 50 because you divided it into half. So the third is excuse me. So the third is 25. So on and so forth. Next, false position. False position, also called the linear interpolation method, is another well-known bracketing method. It is very similar to bisection with the exception that it uses a different strategy to come up with its new root estimate. So this is the example that I provide. So you can easily understand the meaning of false position. Symbol fixed point iteration. Open methods employs a formula to predict the root. Such a formula be developed for simple fixed iteration, or as it also called one-point iteration or successive substitution by rearranging the function of f of x is equals to 0. So this is the example of iteration calculation. So next, Newton-Raphson. Newton-Raphson method is the most widely used for all root locating formulas. The Newton-Raphson methods can be derived on their basis on this geometrical interpolation. This is the example. This is the example of the Newton-Raphson methods. Next, polynomials are special type of nonlinear algebraic equation of the general form. So, this is the form that I include. So, hindi na kayo mahirapan.
The chapter objectives. The primary objective of this chapter is to introduce you to how optimization can be used to determine minima and maxima of both one-dimensional and multidimensional function. There are specific objectives. First, understanding why and where optimization occurs in engineering and scientific problem solving. Second, recognizing the difference between one-dimensional and multidimensional optimization. Third, distinguishing between global and local optima. Next, knowing how to recast a maximization problem so that I can be solved with a minimizing algorithm. Next, being able to define the golden ratio and understanding why it makes one-dimensional optimization efficiency. Next, locating the optimum of a single variable function with the golden section search. Next, locating the optimum of a single variable function with a parabolic interpolation. Next, knowing how to apply the fminbnd function to determine the minimum of one-dimensional function. Next, being able to develop MATLAB contour and surface plots to visualize two-dimensional functions, knowing how to apply the fmn search function to determine the minimum of a multi-dimensional function. Introduction and background. In the most general sense, optimization is the process of creating something that is as effective as possible. As engineers, we must continuously design devices and products that perform tasks in an efficient fashion for the least cost. Thus, engineers are always confronting optimization problems that attempt to balance performing and limitation. In addition, scientists have interest in optimal phenomena ranging from the peak elevation of projects to the minimum free energy. For example, as you can see in a figure, the optimus are points where the curve is flat. In mathematical terms, this corresponds to the x value where the derivative f prime x is equal to 0. Additionally, the second derivative f prime x indicates whether the optimum is a minimum or a maximum. If f prime x is less than 0, the point is a maximum, and f prime x is greater than 0, the point is a minimum. We have one-dimensional optimization. This section will describe the techniques to find the minimum or maximum of a function of a single variable f of x. A useful image in this regard is the one-dimensional roller coaster. A global optimum represents the very best solution. A local optimum, though not the very best, is better than its immediate neighbors. Cases that include local optima are called multimodal. In such cases, we will almost always be interested in finding the global optimum. Just as in a root location, optimization is in one dimension can be divided into bracketing and open methods, as described in the next section. The golden section search is an example of bracketing method that is very similar in a spirit to the bisection method for root location. Example, a function that asymptotically approaches 0 at plus and minus infinite has two maximum and two minimum points in the vicinity of the origin. The 2 points to the right are local optima, whereas the 2 to the left are the global. Next, we have the golden section search. In many cultures, certain numbers are ascribed magical qualities. For example, we are in the East, are all familiar with the Lucky 7 and the Friday the 3rd. Beyond such superstitious quantities, there are several well-known numbers that have such interesting and powerful mathematical properties that they could truly be called magical. The most common of these are the ratio of a circle's circumference to its diameter pi and the base of natural logarithm e. So although not as widely known, the golden ratio should surely be included in the pantheon of remarkable numbers. This quantity, which is typically represented by the Greek letter phi, was originally defined by Euclid because of its role in the construction of pentagram or five-pointed star. So Euclid definition reads, a straight line is said to have cut in extreme and mean ratio when as the whole line is to the greater segment, so it's the greater lesson. So next we have parabolic interpolation. Parabolic interpolation takes advantage of the fact that the second-order polynomial often provides a good approximation to the shape of f of x near an optimum. Just as there is the only straight line connecting to the points, there is only one parabola connecting 3 points. Thus, if we have 3 points that jointly bracket an optimum, we can fit a parabola to the points. Then we can differentiate it, see the result equal to 0, and solve for the estimate of the optimal x. It can be shown through some algebraic manipulation, that is x sub 4 to x sub 2 minus 1 times x sub 2 minus x sub 1 squared f of x sub 2 minus f sub of x sub 3 minus 2 minus x sub 3 raised to 2 or squared times f of x sub 2 minus f of x sub 1, or all over 2 times x sub 2 minus x sub 1 times f of x sub 2 minus f of x sub 3 minus x sub 2 minus x sub 3 times f of x sub 2 minus f of x sub 1, where x sub 1, x sub 2, and x sub 3 are initial guesses, and x sub 4 is the value of x that corresponded to the optimum value of a parabolic phi to the guesses. So next we have MATLAB function fminbnd. So recall that we described the built-in MATLAB function f0. This function combines several root-finding methods into a single algorithm that balance reliability with efficiency. The fminbnd function provides a similar approach for one-dimensional minimization. It combines the slow, dependable golden section search with a faster but possibly unreliable and parabolic interpolation. It first attempts parabolic interpolation and keeps applying it as long as acceptable results are obtained. If not, it uses the golden section search to get matters in hand. MATLAB session that use fminbnd to solve the problem from example. So, command prompt G is equals to 9.81 and V is equals to 0 is to 55, M is equals to 80, and C is equals to 15, and Z is equals to 100. So, also at T minus C0 plus M divided by C times V0 plus M times G all over C times 1 minus exp times negative C divided by M times T minus M times G divided by C times T. So, command prompt X and F is equal to F min B and D, Z, and 0 and 8. So, X is equal to 3.83.17 and F is equal to negative 192.8609. Next, we have multidimensional optimization. Aside from one-dimensional function, optimization also deals with multidimensional function. Our visual image of one-dimensional search was like a roller coaster for two-dimensional cases. The image becomes that of mountains and valleys. As in the following example, MATLAB graphic capabilities provide the handy means to visualize such function. Problem statement. Use MATLAB graphical capabilities to display the following function and visually estimate its minimum in the range. So negative 2 less than equal x sub 1 less than equal 0 and 0 is less than equals x sub 2 less than equal 3. So f times x sub 1 and x sub 2 is equals to 2 plus x sub 1 minus x sub 2 plus 2x sub 1 squared plus 2x sub 1 x sub 2 plus x sub 2 squared. So solution, the following script generates contour and mesh plot of functions. So x equals to linspace negative 2, 0, and 40, and y is equals to linspace 0, 3, and 40. So x and y, we have mesh grid x and y. So z is equals to 2 plus x minus y plus 2 times x raised to 2 plus 2 times x raised to y plus y raised to 2. So subplot 1, 2, and 1. CS is equal to contour x, y, z, and C label is CS. So x label is x and 1 and y label is x and 2. So title is A contour plot grid subplot 1, 2, and 2. CS or surf C x, y, z. X minimum is equal to floor minimum z. X maximum is cell maximum z. X label x 1, y label x sub 2, x label f of x 1 and x sub 2. So title B mesh plot. Figure 1 is the contour plot, the result, and the B is mesh plot result. That's all for part 2. I hope you enjoy and learn from it. Thank you.